The reactions involving gases. So here we're going to bring stoichiometry and gases together. So if we have gaseous reactants or products, we often specify the quantity of the gas in terms of its volume at a specific temperature and pressure. And so we can use the ideal gas law to find out the number of moles or to find the volume of a certain number of moles of gas. And so what we're doing here is at the end of our grams to moles to moles to grams, we're adding another possibility. We already looked at molarity, and so we could calculate the volume given the molarity or vice versa. And now we're going to look at volumes of gases in relation to their conditions, their pressure, and their temperature. So this was the standard grams to moles to moles to grams. So here we're adding a different variation at the beginning and the end. The easiest ones are when the gases are at STP. When the gases are at STP, then you can use the molar volume of a gas at STP and convert from moles to liters that way, and you don't have to use the ideal gas law. Now, if you forget about this or you don't remember the number, you can still use the ideal gas law to find it. It just is a little longer. Pressures in a situation like this could be partial pressures. So just be aware of that. So let's do an example. How many grams of water form when 1.24 liters of gas, that doesn't read very well, of gas H2 at STP completely reacts with oxygen? So we're going to treat these problems like stoichiometry problems because that's what they are. So what we have here is 1.24 liters of hydrogen gas at STP. What does at STP tell us? It tells us the temperature and pressure, and it tells us that we can use the molar volume of a gas. So we can use 1 mole equals 22.4 liters. And they're asking us for how many grams of water. That's what we're trying to find. So our path here is liters of hydrogen. We always go to moles in the middle. To moles of hydrogen, to moles of water, to grams of water. So the basic idea, grams to moles to moles to grams, but we're just tweaking the beginning. We're not starting with grams, we're starting with a volume of a gas. So that volume is 1.24 liters. And we're going to go to moles of hydrogen. And then we're going to go to moles of water. Right. There we go. Got ahead of myself. And then we're going to go to grams of water. Same old pattern. Moles down here to cancel those guys. Moles of H2 down here to cancel those guys. And liters of H2 down here. Moles of H2 to liters of H2. It's the molar volume. It's the volume of 1 mole. It's not that 1 liter is 22.4 moles. 1 mole is 22.4 liters. The middle part comes from the equation. 2 moles of hydrogen get us 2 moles of water. And we need the molar mass of water. 2 times the mass of hydrogen plus the mass of oxygen, 18.016 grams. 1.24 divided by 22.4 times 2 over 2, which is 1, times 18.016, 0.997. grams of water. Questions? Yes? Where does 22.4 come from? Good question. That's the molar volume of a gas at STP. We just introduced that a few minutes ago. So that's a new thing. That's an often overlooked conversion factor. And then, so some students forget that it exists and forget to use it, and then other students want to use it all the time, and you can't use it all the time. You can only use it at STP. If it says at STP, you can use the 22.4. If it doesn't, if it gives you other pressure and volume or temperature or something, then you can't use it. Any other questions? Here's another one. Engineers use copper in absorbent beds to react with and remove oxygen impurities in ethylene used to make polyethylene. Background material. The beds are regenerated when hot hydrogen reduces the copper to oxide, forming the pure metal and water. What volume of hydrogen at 765 torr and 225 degrees Celsius is needed to reduce 35.5 grams of copper to oxide? Can we do that? Sure we can. We can do that. We're going to need a balanced chemical equation, aren't we? Yeah. What are the reactants? Copper 2 oxide. So copper 2 oxide, copper 2 means it's got a +2 charge. Oops. It's got a +2 charge, and oxygen has a -2 charge. So that's going to be CuO. What does that react with? We're talking about regenerating. It reacts with H2. And what does that form? The pure metal, so Cu and H2O. So what we're calculating is the regeneration of the copper bed, not the reaction of it with oxygen removing impurities in ethylene. So sometimes you have to chop down a few of the trees in this forest of words to see what you really need to look at. Yeah. Look at that, and it's like, oh, look at that. It's balanced without any coefficients. Is that possible? Yes, it is. We don't usually give you those on homework or tests or something, but it happens. Some of them are just 1 to 1 to 1 to 1. So we're okay. So what are we trying to calculate? Yeah, what volume of hydrogen? So liters, question mark. Is this at STP? No, that would be too easy, wouldn't it? This is at 765 torr and 225 degrees Celsius. What volume of hydrogen is needed to reduce? And they're giving us a mass of copper 2 oxide. So we're going to write that mass over here, 35.5 grams of that. That's where we're starting, exactly. So this is where we're going, and sometimes we identify where we need to go first, and then we try to figure out where we are. And sometimes we figure out where we are, and then we identify where we're going. It doesn't matter which you do first, as long as you've got them both in place. Don't start calculating till you know where you're starting and where you're going to end up. It's a waste of time otherwise. Okay, so let's just think about stoichiometry, and we're starting with grams of CuO, and from that we're going to convert to moles, because we always go to moles in the middle, from moles of CuO to moles of hydrogen, because that's the thing that we have a question about. And from moles of hydrogen, we're going to liters of hydrogen. So let's plug these things in here. Bless you. 35.5 grams of CuO. And we're going to moles. And then we're going to moles of H2. And then we're going to liters of H2. You need to stop me when I do dumb stuff like this. There. Oops, I accidentally erased. Oh, let's just erase the whole thing. It's H2, it's not H2O. Get carried away. We'll put our units in here. And moles of CuO and grams CuO, and everything's canceling out so beautifully. Moles to moles is really easy on this one. It's 1 to 1. Grams to moles for copper oxide, we find the mass of copper 63.55, and we add the mass of oxygen, 16. And so the molar mass for that one is 79.55. And then we're left with that last term. Do we know the relationship between liters and moles for hydrogen under those conditions? No. What are we going to do? We're going to need to use Pivnert, right? To use Pivnert to find the volume, we need the number of moles, right? So maybe we're going to have to adjust our calculation a little bit here. If we stopped right here, what would we have? Moles of hydrogen. So I think that's what we need to do. So I'm going to erase this. Oh, that's the wrong part, but hey, I can undo it. I'm going to erase this part. I'm going to stop here. This is going to be moles of hydrogen. And so that's not actually canceled out anymore then, is it? So this will be moles of hydrogen. Then I could plug that into PV equals nRT with the other information and find the volume. And that's what we have to do. So 35.5 divided by 79.55 times 1 over 1 gives us moles of hydrogen of 0.44626 moles of hydrogen. So again, I need some space, so I'm going to make some space. Maybe I can get away with just the top up here. We'll see. So PV equals nRT rearranges to V equals nRT over P. So we've got our number of moles, 446. 0.4626 moles. And we know what the ideal gas constant is. And we can't plug that temperature in, right? Because that's not in Kelvin. 225, we have to convert to Kelvin by adding 273. This is equal to 498. So we've got 498 Kelvin up here. And what do we need to do to that pressure? We need to convert that to ATM. And so we've got 1 ATM over 760 torr. So 765 divided by 760. 1.0066 atmospheres. And this, oh, these get long. 1.0066 atmospheres. So we got 0.446266. No, that's an extra 6. What it says there, times 0.08206 times 498 divided by 1.0066 equals, this should have 3 significant figures, so we're going to end with 18.1. 18.1 liters. I almost put grams. It's like, wait a minute, what are we calculating? Volume. There's something else I was going to say about that, but I forgot what it was. Any questions? I am squeezing all these calculations onto one PowerPoint slide. I would encourage you to use plenty of paper when you do these. Plenty of space. Brief review of properties of gases. They expand completely to fill their containers. They take on the shapes of their containers. They have low densities, much lower than solids or liquids. They are compressible, meaning you can squish them into smaller volumes. And mixtures of gases are always homogeneous. I think that maybe just belonged with the next section, but there it is.